All right, let's start talking about Hess's law. And Hess's law are usually considered fairly fun problems. Um, they're not they're not really like anything else we study in AP chemistry. Um, Basically, Hess's law is that if a reaction is carried out in steps or can be carried out in steps, that the actual delta H, okay, for the overall reaction would be the sum of the actual individual steps. All right, it's just a different way to calculate delta H. All right, when is it used? It's used when delta H's are too difficult to actually measure manually. And remember this whole idea of a state function. Because enthalpy is a state function, it doesn't matter what path we go on, as long as we actually get to the same place. I'm always kind of get a chuckle out of there must be some program that picks these little clip arts, and they're obviously going off this whole idea of the state. And that occurs throughout the school year, that there must be a program that takes some hot letter words and actually finds pictures. So no, we're not really talking about geography or politics or anything like that, any type of social studies, but you know, it is what it is. So delta H being a state function, it doesn't matter what the pathway we take as long as we get to what we're looking for in the end. That's all that's important. All right. I'm not even going to really spend much time on this. Okay, enthalpy is an extensive property. Enthalpy for reaction is equal to the magnitude of the opposite sign. Okay, well, number 2 means that if we switch directions, the enthalpy stays the same. It just is a different sign. The state, okay, or phase is extremely important. For instance, if we build H2 plus O2 yielding H2O, it depends on what, and we've said this before, it depends on what state each reactant and product is in to whether what the values will actually be. All right. Molar ratios, what this means is that you can multiply. And I really don't want to spend too much time on these guidelines. Let's actually start doing a couple problems here. Okay. I'm looking for the delta H of this reaction. Okay, and I don't have any value. That's what I'm looking for. What is the delta H? I don't know. But I'm giving these two other reactions that do exist with their delta H's. And the way we actually accomplish this is you just slow it down and you find unique aspects of each reaction. Okay, so I'm trying to match these two with this first one. And a unique aspect that's unique only to the first reaction and this top reaction is N2. When I'm looking down at the third one, a unique aspect of the third one would be our NO2. And what I mean by that is it doesn't show up in the other reaction, but it does show up what we're looking for. And you can see that in order to combine these two to get our reaction that we're looking for, all we have to do is actually just add our two reactions up. Okay, when you add your two reactions up, what's going to happen? Well, let me just erase a lot of this, get it out of the way. When I add up these two reactions that are given, well, since I'm not flipping or multiplying, I can just look at it. I'm going to have these on the same side and these on, well, I'm sorry, on different sides. So my overall reaction will be those two reactants giving off this product, which is exactly what I'm looking for. Okay, so this delta H of this reaction is just quite simply going to be 180 kJ plus a minus, I know it's a little redundant, basically minus 112 kJ. So if I get these two, run this through my calculator, looks like I'm going to be 68 overall. Okay, that one's almost so easy that it's hard to see. So let's see what they have on next. I believe our answer was 68, so it would be A. Alright, a little bit harder. DH stands for delta. Okay, given the following data, calculate delta H for this reaction. Alright, well, again, I'm looking for unique aspects. This first reaction, the C2H6 is unique. But note we have to do some math on this. Well, we have to orientate the reaction to the best of our abilities in order to get it to match. What I mean by that is my C2H6, it matches, and that's unique. That's great. But I don't need 2. I need 1. And I don't need it to be a reactant. I need it to be a product, right? I need it over here. So in order to do that, I'm going to flip the reaction and divide it by 2. Okay, if I do that, I'm going to get CO2, instead of 4 CO2s, 2, plus 3 H2Os, yielding C2H6 plus 3.5 O2. Okay, now my new delta H, okay, and it seems like I lost everything here. I had 2 CO2s plus 3 H2O, just to quickly throw it back down there. C2H6 plus 3.5 O2. My new delta H for this reaction is going to be not a negative 3,120, but a positive. Why positive? Because I flipped it. Okay, remember the amplitude is the same, but the sign changes if you switch directions. So this is a positive, and because I divided them all by 2, I'm going to divide it also by 2. Well, that gets rid of my reaction. Okay, gets rid of my reaction. I replaced that reaction with something I could use. Quickly looking at the other reactions for something unique, I can see that carbon is a unique aspect of the second reaction, but I need 2 carbons instead of 1, so I'm going to multiply the whole reaction by 2. I see in this one that H2 is a unique contributor, but this is where it's a little tricky. I don't need 2 H2s, but 3 H2s. So in order to get rid of it, I'm going to multiply it by 3 halves. Okay, I don't have to do any flipping or anything. Okay, and now hopefully you can see that I have all my reactions all set to go. It might be a good idea to actually distribute these values and do the math. And if you take the summation of my 3 values here, we should actually have an answer. And just to eyeball it, just to spitball it, looks like I have 1,500. Okay, minus, I'm going to call that 4, so it'd be 800. So I have 700 left. And then I'm going to do a minus 750. Okay, so our value is going to be pretty close to 0. Okay, just to see if this was multiple choice math, I'm going to add these values up. I'm going to call it positive 1,500, and then I'm going to subtract 800, and then I'm going to subtract, and you could almost call this, well, since I rounded this one up, I'm going to round this one to 550. 550 times 3 is 1650, divided by 2 would be 825. Alright, so when we actually do our math on this, I'm going to have, doing these two, a positive 700, and then I'm going to have a negative 125. Let's see how close I did. I haven't seen the answers yet. Alright, I'm assuming it's going to be negative 86. That's the closest one, and you have to remember I did a little bit of rounding, okay, as if it was a multiple choice. But I feel fairly confident that it's going to be one of the 86s. I would have to do a lot of rounding to get to the positive 86. So I'm going to call my answer D. Okay, it might actually be E. I might have done too much rounding, but you get the picture. If this was a multiple choice, you'd be perfectly well at ease for doing the rounding I did. All right, I don't know if I'm going to do another one of these. Has this a lot of problems. Hopefully you get the point. Just a glance at this one, I can see that it's another one of those, perhaps using fractions to get rid of things. Okay, it looks like this first reaction, hopefully you can see I'm just going to flip it. Okay, so I have to multiply this one by -1. Second reaction, I'm looking for carbon, so I'm going to just multiply it by 2. Third reaction is a cleanup reaction, I believe. No, actually it's just for the H2s, and it's good the way it is. So there's my math for that. I have a positive 1300. Okay, I have my 800 again, negative. And my last one is going to be a negative 285. Okay, which leaves me about, okay, what is that going to be? 1085. So we're looking at 215. Okay, or roundabouts. All right, so we're looking at B for an answer. Okay, again, it's just that I don't have my calculator on me. So I'm doing a little bit of roundabouting on the answers. And another one that I think we can manage. Sometimes I will say this much. Note that you have maybe perhaps a little cleanup here with these oxygens on the bottom. I guess we'll just do it. Unique aspects of the first one would be our NO, so I'm going to leave that go. I have to get rid of my ozone, okay, and that's what I'm referring to. In some instances, nothing in the second reaction here that I'm working on is actually unique. It's just a cleanup. It's a cleanup reaction to get rid of my ozone. Okay, so sometimes that actually occurs, that it doesn't actually match the reaction you're looking for. So I have to flip it to get rid of my ozones. And this one is going to be, it does have a unique aspect, the oxygens. Okay, I shouldn't say oxygens, the elemental non-diatomic oxygen, which would be this guy. So I have to flip this and divide by 2. Or divide by 2 is multiply by half. Alright, so math-wise, I don't know why I'm not using the tablet. You can see my handwriting just fall apart before your eyes. The first one was okay at 200. Okay, so I'm just doing my mental math again. 200, and then I'm going to do plus 142. And then I'm going to do subtract half of 500, so I'm going to do 250 negative. So I got negative 450 plus a 142, which I'm going to call 150. Okay, so I have negative 450 plus a positive 150. Looks like I'm getting to about negative 300 on the scale. See how close I actually am with my guess. All right, it looks like negative 304. You can see that it's actually, that quick estimating is actually really good at coming up some decent answers pretty quick. Okay. Ideally, you might want to think about when you're doing estimating for multiple choice. If you estimate one thing up a little bit, you might want to go out of your way to try to, round something downward in order to compensate. A couple more slides. Okay. Enthalpy of vaporization. Okay, vaporization is boiling, and it's not truly a chemical reaction. It's more of a process, the process of boiling, okay, accomplishing the phase change. All right, so we have actual reactions for what I'm talking about is H2O going to H2O, but this is a gas, all right, and this is a liquid. This would be the HVAP for water. Fusion, okay. Fusion is melting. So when you think of fusion, it's melting. And I could write the same thing. It would be going from solid to liquid. Combustion follows the combustion reactions. All right, so there's a heat of combustion for a lot of our fuels. Okay, and I think this is the last thing, this whole idea of getting our actual heat of reaction from the enthalpy or the heat of formation. Enthalpy and heat are synonymous. Okay, the heat of formation of a substance is basically how much energy was given off or released when a compound was made. Okay, and it's true for all compounds. Okay, and it's you know, there's something going on here with the state of things. You know what the state is, temperature, pressure, and all that. We usually do things at standard. Okay, standard states, and the naught there also means 25 degrees Celsius. Okay, standard temperature. Okay, standard temperature is different than the STP temperature of 0 degrees. Our thermodynamic standard is 25. Okay, and what we're actually doing here is we're finding out the heat release for building 1 mole of a compound. Okay, that's actually important, the 1 mole. And let me show you really quick what I mean by that. So if we have a water, we're building waters. And states are important, so I'm going to say these are all gases. The balanced equation is this. But this is not how we actually would do a heat of formation for water, because it's to form 1 mole. So in order to form 1 mole, I have to write fractional. Okay, whenever you're doing a heat of formation reaction, you're doing, and I'm sorry, that's not half, that's 1. This is the half. I'm looking at the wrong one. Whenever you're doing heats of formation, you have to do 1 molar increments. Okay, when you do 1 molar increments, okay, and again, these are all gases, this top one is the one you're looking for, because you have to do 1 mole increments for your actual product. And that actually changes all of the values. Okay. Heats of formation. First thing you have to know is that pure substances don't have to be made. Okay. Pure substances don't have to be made. They just, and I went a little too far. They don't have to be made. If the way they come in nature is that form, then there is no heat of formation for it. Okay, what I mean by that is when you're talking about elemental, anything that's just an element, you look up an appendix for the heat of formation for oxygen gas. Well, it's going to be equal to 0. It's going to be equal to 0 because oxygen gas is already in that standard O2 gaseous state. So it doesn't have to actually be made. Okay, that's the way it comes. So what I'm saying is the elemental form of anything would be 0. Now this becomes important when we're actually doing our next step, and that is to calculate enthalpies of reaction from these values of heats of formation. Because when you're, and I realize I'm coming in here on my 20-minute deadline, when you're dealing with a reaction here, and I'm going to put one up really quick, CH4 plus O2 yields CO2 plus H2O. Okay, and these are in the gaseous form. Well, in order to come up with a heat of reaction here, what I can do is I can take the summation, that stands for summation, the big E, of my products, okay, of my H2O, my CO2, and I got to balance this out. And I'm going to subtract the heat of formation for all my reactants, my CH4 and my O2. And what you do is you're going to look up all four of these values in an appendix. I'll give you a big tip here. Oxygen's value is going to be 0. And you're going to multiply, basically multiply the coefficient by the value in the appendix, and then subtract. Okay, products minus the reactants. So you add up the summation of the product side, and then you're going to subtract it from the reactant side. These are usually very, very enjoyable problems. Nobody really dislikes them. Okay, they're usually free points. You hope that you get them. Let's see if we can actually get a practice problem. And I don't think I can because I don't have my table handy. Okay, so we'll do one of these in class. I see I'm 1 minute over. But enthalpy of reaction from the heats of formation are traditionally, like I said, an enjoyable problem to actually receive and to do. So we'll see an example or two in class.